it's about is looking at different scenarios and figuring out how many combinations of those scenarios or how many processes would be possible or options would be possible. And we're just going to start out with the fundamental counting principle. Okay, so first example, Joe is shopping for a car. The dealer says that he has 3 different models and each model could be available in 5 different colors. So the tree diagram on the right is showing how those options are separated. So if Joe chooses Model 1, Model 1 has blue, red, purple, white, or black as an option. So that means there's 5 choices for Model 1. Okay, Model 2, again the same color option, so there's 5 options for Model 2. And Model 3, it could also be available in blue, red, purple, white, or black, so there's 5 choices for Model 3. So in total, if you were to count all of these choices, how many choices does Joe have? 15. And rather than individually counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, what would be an easier way? We would use the fundamental counting principle, which is multiplying the number of options times the secondary number of options. So we had 3 models times 5 color choices. That gives us 15 choices possible. So let's try the next one. Actually, I'll go through the definition with you first. So if we have a process that's made up of several tasks or several stages, basically rather than calculating and counting all the different options separately like we just did in the tree, we can multiply the options for each stage. So if the number of choices for the first stage is A, the number of choices for the second stage is B, and the number of choices for the third stage is C, then the way that we can calculate the total number of options would be A times B times C, and that's the fundamental counting principle. Okay, so it's just shorter than adding them all up. So let's see if we can put that into practice. We're going to compare the tree diagram to the fundamental counting principle. So a toy manufacturer makes a wooden toy in 3 parts. Part 1, the top part may be colored in options red, white, blue, or pink. Second part, which is the middle part of the toy, can be orange, purple, or black. And the third part, which is the bottom part of the toy, would be yellow or green. So we have a few options. As a tree diagram, let's separate this as part 1. Part 1, we have 4 options. It can be red, it can be white, it can be blue, or it can be pink. Part 2, the middle part of the toy, it says that it can be orange, purple, or black. Okay, so if we were to choose the first part as red, then the middle part would be orange, purple, or black. But what if we chose the top part to be white? Then we could choose the middle part of that toy as orange, purple, or black. And the same thing will occur for the blue top part. We could choose the middle as orange, purple, or black. And lastly, if we chose the pink option, the middle part could be orange, purple, or black. The third part is the bottom part of the toy. And the bottom part has 2 choices. So that means if I chose a combination of a red top and orange middle, then I could have the bottom as, yellow or green. And for each option, I have a sub-choice for the bottom to be yellow or green. So I'm just going yellow, green, yellow, green, yellow, green. Now, what if you're designing your house and you want to think about all the different possible choices for, say, your kitchen? Okay, how many cabinet options would you maybe have? How many paint colors would you have? Thousands. There's so many choices. So, do you really feel like making a tree diagram to figure out how many possible choices, if you care how many choices you possibly would have? No. So using the tree diagram, we have to individually count how many choices, and when you count them up, you get 24. Whereas if we use the fundamental counting principle, part 1 had 4 choices: red, white, black, or pink. Part 2 had 3 choices: orange, purple, or black. And part 3 had 2 choices: yellow or green. All we have to do is multiply each part and we get the total number of options. 24 choices. So one term that's very important from the fundamental counting principle is the term and. Anytime you see and, that means multiply. So for the toy had to have part 1, or a choice from part 1, and a choice from part 2, and a choice from part 3. Whenever you see the word and, you got to think multiply. Okay? So let's apply the fundamental counting principle that have restrictions. Oh, sorry, let's do this example first. Math 30 quiz consists of 8 multiple choice questions. Each question has 4 choices. So for question number 1, there's 4 choices. And for question number 2, there's 4 choices. 3, there's 4 choices. For question 4, there's 4 choices. Question 5, there's 4 choices. For question 6, there's 4 choices. For question 7, 4 choices. And question 8, there's 4 choices. So this is and, okay? Question 1 has 4 choices, and question 2 has 4 choices. Question 3, they're all ends, which means we have to multiply 4 times 4 times 4 times 4 times 4 times 4 times 4. Simplify it, 4 to the power of 8. It's a little bit easier to calculate. And what's 4 to the power of 8? We get 65,536. So if they have the same number of choices for a certain number of questions, just 4 to the power of 8. Alright, sorry, what I was getting to before. Now we're going to look at the fundamental counting principle where there's some restrictions. It's important to note that when there's restrictions, deal with those first and then apply the other conditions after. So Eric has been assigned a task of determining how many odd 4-digit numbers there are. Okay, he has been told that a number such as 5,267 is 4 digits, but if your first digit is 0, it's only 3 digits. Okay, so step 1, we're first going to look at why we would put 5 as the last digit. When you're going through this unit, you're really going to want a highlighter or you're just circling key information. Eric has been assigned the task of determining how many odd 4-digit numbers there are. So what do you think 5 could represent if we have to find an odd number? It's all the odd digits. An odd number has to end with 1, 3, 5, 7, or 9. Okay, so the last digit has to be 5 because there's 5 choices. 1, 3, 5, 7, or 9. So the second step of his work is shown. Explain why there's only 9 choices for the first digit.
Numbers 1 to 9.
Awesome. Okay, so one thing we have to note is 0267. That's a 3-digit number. So can we have 0 as our first digit? No. So not 0. But they're digits 1 to 9. Okay, so far we have 9 options for the first digit. and 5 options for the final digit. What about the second and third?
10.
Okay, digits 0 to 9 and 0 to 9. That means there's 10 choices. And applying the fundamental counting principle, now we just have to multiply. We get 9 times 10 times 10 times 5, 4,500. Odd 4-digit numbers. Okay, Eric has now been assigned the task of determining how many odd 4-digit numbers there are which have no repeating digits. So explain why the first step is still valid but the second is not. Let's just go through and solve. Okay, if it's an odd number, what does my last digit have to be? 1, 3, 5, 7, or 9. So we have 5 choices. Okay, so some important information. It's odd, it's a 4-digit number, and no repeating digits. Okay, the first digit, it can't be 0, and it cannot repeat one of these digits. So how many options do I have? 8. Okay, so not 0 or last digit. So that means 8 options. And if I can't repeat on the next one, I've already used 2 digits, so I have 8 again. Now I've used 3 digits. I can't repeat, so 10 minus 7, or sorry, 10 minus 3, I have 7 choices. And then we just multiply. And from there, I didn't actually calculate that one, if you guys just want to do that as well. You get 2,240. Okay, how are we doing so far? Alright, we have number plates in an African country, and they consist of a letter other than I or O, followed by 3 digits, the first of which cannot be 0, and followed by any 2 letters which are not repeated. Okay, so let's go through. Consists of a letter other than I or O. So our first place in the number plate is not I or O. If you guys can't remember how many letters there are in the alphabet, there's 26. So if it can't be I or O, that means we have 24 choices. Okay, so we've dealt with the I or O. Now it's followed by 3 digits. So 1, 2, 3. The first of which cannot be 0, so not 0. So if it can't be 0, we're looking at digits 1 to 9. So we have 9 options. Okay, so it's followed by 3 digits. Only the first one has a restriction. It can't be 0. Could the other ones be anything? Yep, so we have 10 choices and 10 choices. They're letters.
Yeah, letters.
Where?
It's followed by any 2
No.
letters which are not repeated.
Yeah, but that's separate.
We haven't gotten there yet. So we've started with the first letter, it can't be I or O, then it's followed by 3 digits. So these are my 3 digits. And I'm going to get to those last 2 letters soon.
Oh, that makes sense.
Okay, now those digits are followed by any 2 letters. Boom, boom, which are not repeated. So if this is from the alphabet A to Z, how many choices do I have? 26.
It can't be repeated.
These two can't repeat.
So the next
Doesn't
one's-
matter what that one is.
How do you know?
Because it says followed by any two letters.
Which are not repeated.
And then of these two letters, they're not repeated.
So like if it they couldn't repeat the first one either, how would they word that?
They'd probably say the first one cannot, like, they'd probably say here, consists of a letter I or zero that can't be repeated.
Okay.
So now the last one.
Now 25.
And then we've used one of the letters, so we only have 25 letters left. Now we gotta multiply all this. And you should get 14,040,000 options for license plates, for number plates. So the ability for this African country to expand their population's their number of cars is pretty good. Hopefully they don't get that because that's way too many people. Within one country?
One person got only one car.
Okay, that's true.
It's not that many. You wouldn't be at 33 million? Think of like at homes are gonna like cars.
How many in the population of Canada?
It's been like 33 million or
I have no idea.
It's
something.
like,
Beats me.
something. Yeah, it's
The same as California.
33 million or something.
3.2?
33.
Okay.
126.
Gotcha.
How many mil we got?
I think
That's the same population as California.
It is.
Hey, but that's all across Canada. We're like a huge body of
Yeah,
land.
that's what I'm saying. And California has the same population.
That's crazy too.
California's population. California sucks for living. Don't even tell me.
Yeah, I would never. I
Not
would
for
never
2
visit.
Okay, keep rolling, guys. Let's go. There are 2 routes from Pitland
We rolling.
to Queensville. Okay, so 1, 2 routes. Guys, there's 3 routes from Queensville to St. Luke's. 1, 2, 3. There's 3 routes from Pitland to Rutherford. 1, 2, 3. And 1 route from Rutherford to St. Luke's. How many routes are there from Pitland to St. Luke's passing through Queensville? So from P to S passing through Q. Well, let's take this bottom route first. Bottom route and then the top route, that's 1. Bottom route and then middle route, 2. Bottom route, then bottom route, 3 options. Now, top route,
Yeah, multiply.
1, 2, 3. So there's in total 6 routes. What are we doing with these 2 numbers? Multiplying.
I just look so obvious. You guys can do it.
Alright, now how many routes are there from Pitland to St. Luke's passing through Rutherford? So again, we could just map out all the routes or we could just multiply. 3 times 1? 3.
It's not bad.
So how many routes are there in total to get from P to S? There's 6 on the high path, 3 on the low path. Add them together, you get 9.
Oh. That one kind of seems like a good one.
Which area did you take? That's blowing your mind.
So the second really important word, guys, we only have like 5 minutes, so just bear with me, please. The second really important word that we need to pay close attention to is the word or. Anytime you see the word or, that means you are adding. Okay, so to get from Pitland to St. Luke's, we could take the top route or the bottom route. And that's why we have added, because it's an or. Okie dokie. So telephone numbers allocated to subscribers in a rural area consist of one of the following. So the first option or the second option. So we're going to have to figure out how many options for the first one, and then we're going to add it with the number of options for the second choice. Okay, so the first scenario we have as our first 3 digits is going to be 3, 4, 5. So there's only one choice for that. Okay, that's non-negotiable. It's going to be 3, 4, 5. Okay, then it's followed by any 3 further digits. So if we have any digits, that's 0 to 9, 0 to 9, 0 to 9, give me 10, 10, 10 choices. And then we multiply these to figure out what's the total amount of choices for those phone numbers. We have 1,000.
Good afternoon, Mountaineers. It's time for announcements. A reminder that Edge Pink shirt order forms are due in the office by Tuesday. Order forms can be picked up in the office. And a happy birthday to Zoe Christie Down and Bree Kennedy over the weekend. Have a fantastic weekend, Mountaineers.
They said Bree Kennedy, but then they said over the weekend.
Okay, the next scenario, we start with the digit 2. So there's one choice for that. Followed by one of the digits 1 to 5. How many digits for 1 to 5? 5. 1, 2, 3, 4, 5. If you have to use your fingers to count, do it. Okay, followed by any 3 further digits, so 10, 10, 10. We have to multiply these. We get 5,000. What does the term or represent? We're going to add. So 1,000 plus 5,000 gives me 6,000. Possible telephone numbers. Okay, we'll pick up example 7 tomorrow. On Monday.